Welcome, everybody. I am Isabelle Maigret from the Global Sustainable Electricity Partnership. Thank you for joining us for this webinar, in which we'll present findings of the study, Europe's Energy Transition, Sustainable Paths for Increased Climate and Energy Ambition, realized by Enel Foundation, Compass Lexecon, and Enerdata. This session will start with a presentation by your two speakers, which I will introduce in a minute, and will be followed by a question period. If you have any questions or concerns during the presentation, you may use the chat box, which you can find at the bottom of the screen. We have two distinguished speakers today. Daniele Agostini, Head of Energy and Low Carbon Policies for the Enel Group. He's responsible for policy analysis and corporate position development on energy policies and low carbon policies across over 30 countries in which the Enel Group operates. In such role, he's in charge of monitoring and assessing energy policy developments in the areas of energy markets, climate change, renewable energy, and energy efficiency. Mr. Agostini is a member of the board of the International Emission Trading Association. He currently chairs the Euroelectric Electrification and Energy Efficiency Working Group, the Energy Transition, Sustainability, and Climate Change Committee of the Mediterranean Energy Organization, and the Energy Markets Committee of the G20Y. Then we have Giuseppe Montesano, the Deputy Director of Enel Foundation. Mr. Montesano graduated in mechanical engineering and specialized in energy transformation and energy systems in 1985. After experiences in the electromechanic industry, he has worked for Enel since 1988, developing renewable energy projects, designing environmental and low carbon strategies for the group, and advising on regulatory matters. He has covered several managerial positions, including network and tariff regulation, head of environment, head of European regulation and scenarios, head of European energy policy. He also chairs Euroelectric's Environment and Sustainable Development Policies Committee and is vice chair of the Italian National Committee of the World Energy Council. Without further waiting, I will now leave the floor to Daniele.
Thank you, Isabel. And again, I'd like to thank GSEP for hosting this seminar on a topic that in Enel we hold very dear to our heart. Climate change is a real issue, is becoming urgent, and we need to accelerate the energy transition. And that is the spirit with which we embarked into this project. When I say we, I say the Enel Group, but a real player here is the Enel Foundation. The Enel Foundation is focused on exploring the most significant and the structural changes in our society, especially on the medium to long term. And in that way, it encourages stakeholder dialogue in this area. So the Enel Foundation, together with Enerdata and Compass Lexecon, did this research, which I find very interesting, and I'm glad to share it with you. So let's go on to the next slide and look at some of the background of this research project. So the context is, of course, the context of the Paris Agreement, as I was mentioning earlier. It's a context where climate change is more and more urgent, and we need to increase ambition. And so with this project, we explored the possibility of increasing ambition in Europe, raising the target to 2030 to 50 to 55%, and going for carbon neutrality by 2050. Now, of course, this is in line with the proposal that the European Commission presented last year with the European Green Deal and the more specific communication that we had in the spring. However, this is also in the context of the pandemic crisis that is taking place, the economic recovery plan that was launched in Europe, and the Green Deal investments, but also carbon border tax discussions that we're having in Europe on how to make sure that the increased ambition is compatible with economic sustainability, but also, as we will see, social sustainability. We think the research is particularly timely because it comes in the same context of recent development that have seen technological progress and cost reductions really accelerate the penetration of clean technology on the market. At the same time, national energy policies and regulation are also accelerating the energy transition. This is in light of other policy drivers that we see are becoming more important, or increasingly more important. I wouldn't say more important than climate change, but increasingly more important, and include air quality, security of supply, circular economy, but also issues such as green growth, actually creating employment through the energy transition. We've also seen digitalization really change the context in which we operate, creating new business models that are accelerating the penetration of these low carbon technologies and zero emission assets. So in this context, again, this study has explored how more ambitious decarbonization objectives can allow Europe to decarbonize. It has looked in detail what the role of the power sector is within this decarbonization, and also assess the impacts on costs, investment costs, but also total energy system costs of this energy transition. So let's go on to the next slide. The model was set up to explore two basic scenarios. A reference scenario, which was looking at the current set of climate targets, the one set by the Clean Energy Plan, and a decarbonization scenario which was actually looking at increased ambition targets that were proposed with the European Green Deal. Now, the first set, the reference scenario, was using the old targets with the same cost curves that we had observed back 5 years ago when the Clean Energy Plan was being developed. Whereas the decarbonization scenario was doing a stock taking of the recent developments that I mentioned earlier. And so the reduction in cost of renewables, for instance, of electric vehicles, of batteries. On top of that decarbonization scenario, the project also ran a sensitivity reference scenario, which actually explored what the world would look like if we pursued the same policy targets that we had before, but with these renewed costs. So obviously it's an intermediate outcome, but it was very useful to try to get a sense of how the curves were changing. Of course, for each scenario, every sector was looked into, and especially there was an effort in trying to map the key enablers in terms of technology, regulation, and business models that would enable the energy transition to take place at a faster rate. The impact assessment was performed, identifying key performance indicators that could describe the impacts that this energy transition would have on the different sectors in terms of both the technology mix and the costs. So again, there was a big effort on one hand to align these scenarios with what was done by the European Commission in order to enhance comparability. And on the other hand, there was a very prudent approach in trying to make sure that the assumptions that were adopted were not too aggressive. We wanted to be relatively conservative. And I think I have to give credit to the Enel Foundation, Compass, Lexecon, and Enerdata in doing that. As Enel, you may know, we have a rather bullish view on the energy transition. We do think that things are going to be happening at a faster rate than everybody expects. But in this project, the Enel Foundation, in order to have a more effective and efficient dialogue with stakeholders, wanted to make sure that the assumptions that it was incorporating in this study were not too aggressive. Next slide, please. Let's look at a bit of the methodology behind the study. Now, we believe that the study is unique, but because it actually combines the use of two models. The Pulse energy model by Enerdata was used to simulate decarbonization across the entire economy, including all the different sectors. But then the CL power model was used to actually do a deep dive on power sector dynamics. A deep dive that was performed with a high level of granularity, going down to an hour-by-hour basis in terms of the time scale, but also dividing the European region in different areas, geographies, sometimes corresponding to actual member states, other times grouping member states, but being able then to create a differentiation that allowed it to tailor the potential, for instance, of renewables country by country, but the same with other key technologies such as batteries and cars. So again, we believe that the results are particularly important because there's this combination of these two models, which is, we believe, unique in this context. Let's go to the next slide. In the next slide, I'm going to give you a bit of a sneak preview on the conclusion. And of course, as they often say, I'm going to tell you I'm going to give you the conclusion and then tell you how we got there, but then repeat the conclusions at the end. And the conclusions are that the increased ambition that was set forth by the European Commission turns out to be indeed achievable. It's achievable in light of the recent technology advances that we have seen in the area of renewables, batteries, electric vehicles. It's achievable also because electrification in transport and building sector is becoming more and more a reality. These technologies are mature and are penetrating the market as of today. It's achievable because new business initiatives based on new business models catalyzed by digitalization are allowing us to reduce drastically the deployment costs of some of these new technologies. Last but not least, it's achievable because new national and local energy policies and regulations are actually accelerating as of today this transition. And I'm referring to coal phase out policies, to the phase out of internal combustion engine policies. These policies are really making a difference in delivering the economies of scale needed to accelerate the deployment of these technologies. So the increased ambition is indeed achievable. It is also affordable. We find that the increase in ambition by 2030 is actually possible even at a slightly lower cost than the original cost foreseen by the clean energy package. This is possible by bringing forward the picking of low-hanging fruits that we would have postponed after 2020 with the reduced level of ambition that we have today. If we look a bit on a longer term, by 2050, costs, of course, become higher because of the increased decarbonization that goes to 100% by 2050. However, this is true in terms of investments costs. If you look at total energy system costs, as we will see, that is not the case. We actually have a stabilization and a corresponding reduction. Now, of course, all of this is in terms of net cost. The trick, of course, will be to make sure that this decarbonization, this energy transition happens in a just way, leaving no one behind. And that is really important to make sure that we do that. Anyways, after this sneak preview, I'm going to pass the floor to my colleague, Giuseppe Montesano, as we move on to the next slide, please.
Thank you, Daniele, and hello to everybody. Let me say, first of all, that having been one of the moving forces that was behind the ancestor of the GSEP, the then called E7 and E8 group, it's really a pleasure for me to be with you today. Now, taking the relay from Daniele, we start to get a little bit in more detail in the results of this study. As anticipated by Daniele, one of the first results was that, as it is shown on this slide, increasing the target GHG emission reductions close to 55% in 2030 is possible and also necessary to achieve net zero emissions in 2050. In this slide, there are two graphs that are shown. The first one on the left tells you that in the decarbonization scenario that we have developed, that this decarbonization scenario that we have developed brings to net zero European GHG emissions in 2050, and to a reduction of approximately 55% in 2030, which is therefore in line with the higher ambition set by the European Green Deal. The right-hand graph allows us to look at the emissions reduction by sector. And we can see that in 2030, the biggest differences between the reference and the decarbonization scenarios are in electricity, which are the green lines, and in transport, which are the red lines. And the latter reductions are mainly thanks to electrification. We are talking in the decarbonization scenario of having on the European roads approximately 64 million electric vehicles, a number which takes into account the inertia in the substitution of the existing fleet. And as far as electricity is concerned, the main drivers are the development of renewable capacity, as we will see in further detail, and the coal phase out. For buildings, the blue lines, and for industry, the orange lines, most of the expected reductions will take place after 2030. If we now move on to the next slide, we see that as the power sector decarbonizes, electricity emerges as the key energy vector for the net zero ambition. Our decarbonization scenario sees a direct electrification rate of 60% in 2050, which is shared among the sectors as 63% for transport, 72% in buildings, and 46% in industry. If we move now to the next slide, since electrification is key for the net zero ambition, net zero will therefore push power demand. And in particular, we see that we will have 38% more power demand in the decarbonization versus the reference scenario in 2050. And this will particularly happen in the transport and in the industrial sector. The transport is the dark blue, and the industrial sector is the light blue in these graphs. The increase of demand in the industrial sector is due also, I would like to underline this, to the electrolysis to produce hydrogen as a feedstock for processes with hard to abate emissions. Moving to the next slide, with an 84% share of renewables and coal phase out, the power sector is fully decarbonized in 2050 in the decarbonization scenario. So as I already said, renewables and coal phase out are the main drivers of a decarbonized power mix. But what I would like to note here in particular is that 74% will be the penetration of variable renewables in 2050 in the decarbonization scenario. And this has, I would like to underline, obvious consequences on the flexibility needs of the system. The next slide shows us that renewable capacity in the decarbonization scenario would increase by 70% in 2050. And this is indeed a substantial increase in renewable capacity, which goes well beyond the current national energy and climate plans in Europe. And I would like here again to highlight some implications of this, some consequences of this. And the main consequence, the main implication is the importance of creating a positive framework for investments in renewables, which continue benefiting from substantial cost reductions that need to be captured. Next slide, please. It will be the first one about some considerations, some results about the costs that we have assessed. First of all, in this slide, we look at the 2030 perspective. And our analysis in this perspective shows that resource mobilization is indeed possible. We have analyzed annual investments and total system costs in the reference and in the decarbonization scenarios, and also in the third scenario that Daniele mentioned before, which combines less ambitious objectives and more optimistic cost reductions. And there are here a few main messages. The first one is that increased ambition in 2030 implies investments indeed, but offers more efficiency, which leads to a lower total system costs. It is to be noted that investments are not very different between the three scenarios, and more ambition will likely allow us to benefit from an acceleration in cost reductions. In the following slide, we look at the 2050 perspective. And in this perspective, the total annual system costs also remain comparable to the reference, thanks to the ability to capture the energy efficiency gains unlocked by electric vehicles, heat pumps, and electrification of industry. But there is a price for this, a price which is the price of full decarbonization, and this is an increase of annual investments compared to the reference. Investments that therefore must be enabled to capture the efficiencies I just mentioned. If we move to the next slide, we look at the some sectoral detail of system costs. And we see that in the 2021-2030 period, which is on the left graph on this slide, costs are comparable or lower in all sectors in the decarbonization scenario compared to the reference. But if we look at the 2031-2050 period, which is on the right hand side, sectors will be affected differently. And in particular, costs will be significantly higher in the building sector in the decarbonization scenario due to the significant investments which are necessary to renovate the buildings. But also significantly lower in the transport sector. And this is an outstanding effect of the great efficiency improvements from electrification. So now I will turn back again to Daniele, who will now look a little bit more into the detail of the power sector results, and in particular, to some key enablers that are related to the flexibility needs in the power system that I also mentioned before and pointed as a key element of these scenario.
Thank you, Giuseppe. And so let's do a couple of proposed model that was very much across the entire economy, looking at all the sectors with a good level of detail, but also in a more aggregated way. For the power sector, instead, the CL model dived more deeply into specific issues, highlighting some of the key enablers that will allow this energy transition to happen as fast as we need it to happen, but also some of the most critical area. Now, the first one that we wanted to highlight is the one on grids. Now, as most of you probably know, a lot of the models that are out there and simulate this type of energy transition do not explicitly simulate the grid transmission and distribution. They tend to look at sectors and vertically at either vertically or in a cross-sectoral way. Now, of course, in order for the results of this model to be comparable to those models that are going to be the subject of a lot of discussion in Europe, even in our case, the models are what we call copper plate model. So they do not simulate the grids explicitly, but they take it as exogenous variables. So they input to our model were actually the scenarios that are published by the Transmission System Operators Association and Group with their views on what's going to happen. And this is also just addressing some of the questions that I've seen pop up on the chat. However, the project does identify the grids as being a key component in making sure that that energy transition take place, and that's for three main reasons. The first one, of course, grids will allow increased penetration of renewables. On the other hand, they will also have to serve increasing electricity demand from electrification, and especially in terms of peak demand, either on a daily or seasonal basis. Last but not least, grids will need to modernize and digitalize, and we know that the rate at which technology is progressing in these areas is significant. And so it is important that grids that have historically tended to lag behind compared to the rest of the power system, I'm talking more generation and retail, do actually keep up. So there's some very good analysis out there. And again, the full study deck will point you to some of the what we found were the best sources. One of the, of course, the most authoritative one is the one of the IEA, and you see here the graph on the right that gives you a sense of the increase in investments, cumulative investments in power networks that will be needed between 2019 and 2040. And so we see an almost 50% sustainable development scenario. If we look at the European level, talking about $1 billion a year of 2019, up to 40, but even maybe ranging to 60 by 2040 billion a year. So very substantial investment. But however, it is investment that brings a number of multiple benefits. So it's not only in terms of climate change mitigation, but also in terms of our resilience to climate change we see around the world in terms of extreme weather events, but also in other times of crisis. And unfortunately, I have to say that even today during the pandemic, having a digitalized modern communication and electricity system is playing a key role in ensuring our economic resiliency to the crisis. So again, grids Sorry about that. And we need to make sure that they actually, the level of investments is fit for the purpose. So let's go on to the next slide, please. And we'll look at instead the role of flexibility on the demand side. As I said, the CL power model, very granular outlook. It goes down to hour by hour. And that is very important in order to explore how, for instance, EV charging through V2G technology can bring efficiency to the energy transition and to the decarbonization of energy consumption in Europe. So for instance, today, we broadly think of charging, more based on either, day or night type of tariffs. If you actually introduce a more dynamic type of modeling of these shifts, and you actually start correlating the demand for charging with the actual seasonal trends for wind and solar, you actually find that this may look slightly different. So on the right, you have what you normally see, your typical dynamic EV charging, which tends to increase during the day when solar power tends to provide a lot of extra electricity that can be stored into batteries, for instance, in cars. However, again, if you increase the granularity of your simulations, you find out that during the winter, it is true you have that peak in charging during the day, but an optimal solution actually sees also an increase in charging in the late hours of the night or early morning, where again, we tend to have certain wind powers and a drop in energy consumption that do create that extra surplus of electricity production. Again, these type of models allow you to do that type of computation and actually estimate in a more accurate way the actual needs in terms of storage and capacity for the power system to electrify energy, final energy consumption. So very interesting on a daily basis. If we look at the next slide, please, we actually see the results of these computations that give you a certain type of capacity that will be needed. And again, you look at the difference between the reference scenario and the upper right, and on the lower, you have the decarbonization scenario. And in the decarbonization scenario, you're actually replacing some of that flexibility that was being provided by open combined cycles, open cycle gas turbines or combined cycle gas turbines. You replace it with more advanced flexibility that is being provided by roughly 270 gigawatts of batteries, over 120 gigawatts of power to gas to power. So we're talking hydrogen, of 40 gigawatts of down those 200 power into roughly 220 gigawatts of large-scale batteries, but then also 10 gigawatts of behind-the-meter batteries, generally associated with PV and solar. We have in those 270 gigawatts also 40 gigawatts of batteries embedded in vehicle-to-grid. Now, again, these are rather conservative assumptions based on conservative methodologies. There will be discontinuities and disruptions in the technological development. So we actually expect these numbers as Enel, we would expect them to be higher. But the project itself, again, was based on trying to have a very prudent approach. Now, again, by exploring the needs for flexibilities, of course, you see that solar peak production dictates the rhythm of the energy cycle on a daily basis. On a weekly basis, of course, wind comes in with its type of variation, which makes it quite interesting. On a seasonal basis, which is one of maybe the biggest challenges that the energy transition is posing, we, however, see that there is a complementary role between the seasonality of wind and solar. So again, during the wind, when you have maybe less solar wind, it tends to blow more and generate and compensate partly for that reduction in solar, and the other way around during the summer. Of course, these meteorological patterns are going to be changing drastically because of climate change, but based on the current patterns, this is some of the findings that we are seeing. If we go to the next slide, please. we actually see again some of that granular simulation on a seasonal basis, which again brings some interesting results. In blue, you have the stock of hydrogen gas that can be used for power to gas to power type of generation. As it accumulates or it's depleted over the year, starting on the left with January and then running throughout the year through December. So you can see that during the winter, because of those wind patterns that we were talking about, you have an accumulation of the stock. Then it starts decreasing between February and March. So that's when you're going to be using your hydrogen or corresponding synthetic gases to generate power. In late spring, energy demand decreases, and that is the time instead that we do have a good wind and solar regime that can be used to, again, restock the reserves of gas, which are then used in during the summer, and then again repleted in the early fall until we get to the full of the winter, where you can see again in December, you start using that gas. So again, this is to give you a sense that the specific meteorological trends within a region are very important in terms of sizing the different parameters of a power system in terms of both renewable energy capacity, but also the need for storage in terms of both daily storage, for instance, through batteries, but also seasonal storage in terms of hydrogen and synthetic gases. So let's move to the last couple of slides where we draw some of the conclusions in order to leave also some time for the Q&A. So on a high level, again, as we anticipated in the beginning, we believe that through this project, we've explored the possibility that increased ambition is indeed feasible because of the technological advances that we've seen in renewables, batteries, storage, the sectoral coupling that we're observing in through electrification and transport and building. It's also starting in the industrial sectors, the new business initiatives, and also the trends in national policies in terms of phase out of coal and the combustion engine. Within this context, the power sector does play a very important role. We see a lot of the cost reductions are happening in the power sector, as we said earlier, as well as the national policies, but also we see a blossoming of the flexibility solutions that are actually allowing the deployment costs of some of the assets to be reduced. What is lagging probably behind are the upgrade of the grids. It is happening very much in certain countries. And again, as Enel, we're a leader in Spain and in Italy, but it is lagging behind in other parts of Europe. This increased decarbonization by 2030 actually lowers overall cost. Investment costs will increase between 2030 and 2050, but as Giuseppe summarized and presented earlier, you see total system costs actually stabilize between 2030, 2040, and then actually starting to reduce. When we look at these costs, however, we must not be misled in terms of the need to make sure that no one is left behind and that any costs that may arise, but also the benefits are distributed in a just way across society. So there should be really a focus on making sure that a just energy transition is implemented by ensuring that transparency of the planning is put in place, full participation, and where costs are being borne by the more exposed segments of societies, these costs are mitigated in order to make sure that the transition is also socially sustainable. If we look at some of the more specific recommendations that we found with this project, and we move on to the next and last slide, we believe that it is important that climate ambition is increased in order to make sure that we are on track to meet the Paris Agreement, but also that we do effectively fight climate change. Of course, also the corresponding targets for renewable energy and energy efficiency in Europe will have to be upgraded accordingly. And some of the KPIs of the study that you will find in the full deck, which is available on the Enel Foundation site, give you some of the numbers for this upgrade of these targets. These policies, of course, have to take into consideration a realistic potential of decarbonization technologies. There are technologies that are already mature. A lot of the electric ones are mature. Others that are still yet to come, such as hydrogen and CCS. And so it is important that we do spend research money on these technologies and don't try to jump ahead too quickly on deployment before the cost of these technologies are reduced. Another important recommendation that we make is technology neutrality should look at the multiple benefits of action in climate and make sure that every investment is actually measured not only in terms of the benefits it brings in terms of CO2 reduction, but also the benefits it brings in terms of air quality improvements, in terms of circular economy, in terms of creating employment, which connects again to the just transition issue that we want to emphasize again, and the cross-sectoral synergies that are also very important. Now, the power sector is in pretty good shape and fit for this transition. Market design probably needs to be upgraded to fit the new nature of the costs of the new assets, which are largely fixed. There's very low variable costs in the new assets that are being deployed. Wind and solar will play a significant critical structural role in this energy transition. So it is key that we work on value chains, European value chains, that make sure that these technologies improve as much as possible. On the market, the role of power purchasing agreements are also very important in providing the finance to deploy these renewables. Electrification of end use of energy is key, and in that area, digitalization plays a key role, especially in terms of infrastructure. When I talk about electrification, of course, there's also a very important role for both, also important role for indirect electrification. Hydrogen and power-to-X technologies play a very important role. The volumes that will be able to be delivered are not as large as some people hope, we think. And so they should be really focused on first, as a priority, on those hard to abate sectors, such as steel, the steel sector, some parts of the chemical sector, heavy duty transport, freight transport, before we start using it on more on other type of uses where direct electrification can actually decarbonize at a lower cost. So again, just to sum it up, increased ambition is possible. We just need to make sure that we stay focused and put in place the key enablers. And one of them, of course, is a just transition. I'll close it here and open the floor for possible questions that may be arising. Thank you very much for your attention.
Yes, thank you, Daniele. I think we have a first question from John Jitao. The scenarios show a 2-degree target, but a 1.5-degree target is more prudent due to the externalities involved. How flexible are the models to adjusting to even more aggressive decarbonization targets? And there's an additional question from Francis Ketende, actually, that could be similar, well, related. Will the cost of the decarbonized scenario be the same as for the reference scenario?
Well, I have a first go. Daniele will answer. Yes. Okay. So, well, the way the study was designed is not a study that looks into the details of the consequences of increase of temperature. what we focused on is directly the targets that are set by policies, because what we wanted to do is to have a kind of call it counterfactual compared to the impact assessment that the European Commission is doing about an increased ambition. So in this sense, the increased ambition is not measured with temperature increase, but is measured with targets on energy efficiency, renewables, and greenhouse gas emissions. So that's what the study does. We, as you have probably seen in one of the first slides, have defined the reference and the decarbonization scenario in such a way that we took into account a certain level of these targets. And this was the reference for the study. To the second question, I'm not sure I understand it because, I will try to rephrase what I perhaps too briefly said during my intervention. The decarbonization and the reference scenario differ in terms of costs. There are, and this is one of the results of the study, there are in fact not substantial or significant differences in a 2030 perspective. And this means the study tells us that we can benefit from a certain reduction of technological costs that has taken place after the reference scenario to increase our ambition at no additional cost, and very synthetically. If you look at the 2050 perspective, there is a difference in the sense that in the decarbonization scenario, you need quite a lot more investments. But then these investments can, in the longer term, lead to a reduction, to lower system costs, because they bring into the system much, much higher efficiencies.
Thank you. We now have a question from Debbie Gray. To allow for increased flexibility, did the study examine the option of increasing transmission capacity from hydropower-rich areas of Europe, such as Scandinavia, to consumption centers as an alternative to battery storage and a possible solutions to interseasonal storage?
Okay, I go first. Also on this.
Sorry, I can also jump in, Giuseppe, just to give you a break. As I said, the interconnection between regions within the models was taken as exogenous based on the results of the scenarios that are done by ENSOE, which of course look at very aggressive scenarios. So in those terms, as you probably know, well, you may not know, the Nordic countries are quite well integrated with the Central European market. Of course, there is some limits. I also saw a question on the role of transmission capacity and the difficulty of building new capacity because of sort of NIMBY type of approaches or just transition approaches. So in that sense, the transmission grid was not modeled explicitly, but it did look at flows between the Nordic regions, so large hydro, and Central Europe. And then of course from Central Europe, there's also repercussion towards Southern Europe and Western Europe. Today, there's quite a bit of flow between the large hydro in the Nordic countries and the somewhat either thermal or variable renewable energy that is being generated in Germany. So in that sense, the answer is yes, to the extent that the capacity set out by ENSOE in its 10-year well, its development scenarios is portrayed. I don't know, Giuseppe, if you want to add something to that.
No, yes, I want to add something, but broadening a little bit the scope of the discussion and to give Debbie an indication of another study that we did at Enel Foundation, which precisely looked into the capability of a strengthened transmission grid, a better interconnected transmission grid to improve the optimal technical economical penetration of renewables in the system. We did this in another geography, the South American geography. And Debbie, if you are interested, I can send you the link also to this study. And for that, we used another model, which is specifically conceived to model transmission systems, and that of course can be used also in other contexts and in other geographies. So again, if some of the participants in this call are also interested in approaching us at Enel Foundation to explore possible partnerships to do studies together, you will be more than welcome.
And again, complexity at simulating the grids and the transmission lines. And so that's why in this project we decided to explicitly take what was a more credible and authoritative view of what can be done in terms of transmission. Of course, that may have some repercussions, but it was a strategy, a research strategy in this case.
Thank you. We have another question from Carolyn May. You talk about ensuring we have a just transition process. Can we share a bit more about how Enel is trying to achieve this within your own company, with either skills training, compensation for workers, as an example? And from an EU policy perspective, what types of legislation do you think can support this?
Well, within Enel, we've identified relatively early on the just transition as being a very important element, both of our sustainable development strategy, which again is environment, economy, and the social dimension, but also in terms of industrial strategy. If you try to do an energy transition without addressing the social dimension, it's a bit trying to accelerate a car while keeping your handbrake pulled. And of course, it creates an extra cost. We are very active, as many of you know. We still have a very significant thermal fleet. Today, half of our fleet is renewables. We still have coal and gas. We're phasing out coal in Italy, in Chile. And so again, we're engaging in, we're getting our hands dirty with the actual transition in these communities from fossil fuels to clean energy. Now, the way we go about it is for our own workers, we do try to make sure that we retrain them and redeploy them in other parts of our business. And again, we are very active on the distribution side. In countries, we're very active in the renewable energy space. Our 15 billion euros in our 3-year plan are dedicated for 2/3 to renewables and 1/3 to grid. So as we're taking our fossil fuel-based assets and redeploying these new use and convert them. For the ways in which we work, trying to engage with the communities to understand what the future could be for those communities. And we're running these big projects, which are called Future E projects, where we try to develop this vision for the community with we're installing some gas plants, open cycle gas plants. In other cases, we're installing solars and renewables. In other cases, instead, we're planning on transferring these sites to new type of uses. Now, from our experience, of course, and we're doing this also working with the value chain by mapping the supply chain, the suppliers that were used in those regions, and discussing with them their future, helping them to convert to our new industrial strategy or to be prepared for other investments. And so we work with the local government in understanding what other investments are taking place in those regions. It's a very interesting area. And I encourage you to stay in touch with us in terms of policy making. We find that too often local government is not connected to the central government. So there's a disconnect between the level of government that needs to be addressed very quickly. Often local government is not seeing these matters as urgent. They're waiting too long to actually start moving onto this onto these areas. So for instance, in Italy, we have a coal phase out by 2025. And often we see people are not ready to really engage in these conversations, but to actually convert these communities to a new green economy. You do need that time. So it's very useful if governments are more active in planning ahead alternative economic activities for the impacted communities, in mapping out and identifying which companies, which people are actually impacted, and then involving them in reskilling programs. And there's some very interesting one. There's a beautiful one in Romania where you're actually reskilling coal miners into wind technicians. And again, sometimes these workers, from resisting change, they actually embrace change because they do see a future for themselves, a future that is actually brighter. And in that sense, they actually help the energy transition instead of resisting it. I'll leave it, but also I would encourage you to look at some of the research that the Enel Foundation has done in this area. There's a very nice study. It's called Just Evolution 2030, which is also on the Enel Foundation site, which actually looks into more detail in what policies can be adopted to address both the impact on energy bills, on workers, but also on the competitiveness of the industry.
Yeah, and if I may, there is also another one that is called equality that also looks into these issues of just transition.
Thank you. I know we're almost at the top of the hour, but maybe we have time for one last question, and we'll also share once again the link to the full report and executive summary in the chat. So if your question has not been answered, you may find more answers in there. So the last question from Ivan Klisch: how increased transmission capacity is necessary to achieve GHG emission reduction to 55%? And how much the difficulty to build transmission lines with social acceptability, by example, limit the penetration of renewable energy in Europe?
Well, again, this study has not, as Daniele explained, explicitly looked at the issues related to the transmission network. What I would like to say, however, is that at least in the European context, what we are highlighting with this study is that if we talk about grids, it is certainly evident that they are very, very important in order to allow for the renewable capacity that we are talking about to get to a net zero scenario, to actually be in the system in a secure and reliable way. But that there is perhaps, at least in the European context, the distribution level that is even more important than the transmission level in order for this to happen. If not because, let's say that in Europe, interconnections are already relatively good, whereas in many areas, distribution grids definitely need strengthening or a more smart approach than what has traditionally been used. So you are in mute, Daniele.
Just to add on that, and you can hear me because I was having some connection problems. The study also, to reinforce what Giuseppe was saying, it's interesting because it really shows with the power sector modeling how a bit of this traditional approach of looking at variable renewables and storage from large hydro, which has a bit of its issues in Europe in terms of new plants, and with the grids is only part of the picture. And it is important to create those enablers in terms of regulation, in terms of incentives for more distributed flexibility with these new business models that encourage batteries, vehicle to grid, because it is a more dynamic flexibility that can actually address system needs on a smaller time scale. So again, as we'll that backbone in terms of it needs to be complemented by these more dynamic to increase the hosting capacity of the system in terms of variable renewables through the flexibility of both the demand and supply side. So that's also very important.
Thank you very much. I think that's all the time we had. Thank you very much, Daniele and Giuseppe, for this insightful presentation. And thank you to all the participants who joined us today. The webinar will also be available online after sometime today during the week. So you can watch it again for more insights. So thank you all to everybody for joining, and have a great rest of the day.
Thank you.
Thank you, Isabel and GSEP, for hosting us.